Okay, so we're doing 41 through 50 for the 2015 local exam. And here, for 41, it looks like you need to do math. You're given a bunch of numbers. Your answers have to do with numbers, but really you do not have to do any math. It's completely conceptual, and the reason that is that they're looking for you to make a stoichiometry mistake and multiply everything by 4, because you can see that 59 times 4 is 236, but in electrochemistry, you need to know that no matter what coefficient you multiply an equation by, the voltage change is going to be the same from products to reactants, so it does not matter. So you automatically X out the 236 millivolt options, because you're not going to be multiplying by 4. And so you can see if you're increasing the pH, you're lowering the H plus concentration. So that means you're going to be shifting this equation to the right, and that means Q or K, technically K, because we're not at weird conditions, right? But either of those would be increasing. And if it increases, the voltage needs to actually decrease, because if we look at the Nernst equation, oops, why do I have two equal signs? You usually use Q, but if this increases, then L and Q increases, and then you're just subtracting by a larger number, so E would actually decrease. So that's how you get A. 42, what is the KSP at this temperature? Okay, so looks like it's going to be you find delta G's, and then you use Hess's law, and then from the overall delta G, you need to get K. So the KSP, so essentially what we have to do is we need to eliminate the 2 Ag plus from the or 2 Ag solid from the right side and substitute it with 2 Ag plus. So what we're going to do is multiply this equation by -2. In other words, that means flip the equation and multiply by 2. So our voltage for that, remember, don't get it confused. You're not multiplying by 2 for the voltage. It's not a enthalpy value or anything like that. It would just be negative 0.799. So, and the reason you don't do that is because when you're doing a delta G equals negative NFE, we can put standards on this, the N takes care of the stoichiometric part. So that's the reason why you wouldn't automatically put in the E already. So if we do this for the top equation, we'll get delta G is equal to negative N. So that would be 2 because we have 2 electrons transferred. Sorry, I don't have my calculator with me today, but I'll try to go through the expression writing of the math, but I can't like do the brute math, but if you've got your calculator with you, then that's obviously fine. So that's your delta G value for the first one. Then your delta G value for the second one is, this time it is -2, because we did multiply the thing by 2, so we're transferring 2 electrons instead of the 1 that it presents to us. This is how we take care of the stoichiometric part once again. Then here we have negative. Oh, I don't know why my decimal sign is before my negative sign. 0.799. So that's how you find the individual delta G's. Then you would add them up, and then you get like delta G overall. And then from that, you can say that delta G overall is equal to negative RT ln KSP. And the reason it's KSP in this case is because your equation is literally the composition equation for KSP. So that's how you get KSP. This R is 8.3145. Don't get it confused with this or this. This is energy R we're talking about, so it's not these. This is temperature in kelvins, so basically you just solve from here to get KSP, and that would be C. Once again, I just don't have my calculator, so I can't do the brute math here. Okay, but moving on to 43. 41 and 42 were mostly conceptual. Like, obviously calculations were involved, but you need to know what to do first, right? But then going forth, we have basically memorization or just prediction questions. So what's the value of the angular momentum quantum number for a 5p orbital? We don't care about the 5, that's n, and then the p orbital relates to the L. So we have S, P, D, F, GH, and so on, but those don't really matter. 0, 1, 2, 3, 1. So it's A. 44, which has chemical properties most similar to those of P. So we're probably looking for elements that are also in the group that P is in, which I think is group 15. So our choices are nitrogen, aluminum, sulfur, and arsenic. So if we go up, nitrogen, aluminum, sulfur, and arsenic, and then this is what we're comparing to. So I think we would automatically eliminate aluminum and sulfur, and from here we got to choose between two members of the same group, but I think you would go with arsenic because if you didn't know, starting with the third period, you can have extended octets, right? You can disobey the octet rule and not have things go completely wrong. So that in that sense, P and AS will have more bonding similarities and reactivity similarities than N and P will. So you would choose arsenic. 45, which has the lowest melting point. Generally, I think metals of the same group, if you go down the group, you have lower melting points. So you would choose rubidium because it's lowest in group 1. 46, which gas phase atom has no unpaired electrons in its ground state? I'll just show why it's beryllium, since that's probably all that's necessary to explain. So beryllium has this electron configuration in its ground state. There's only one s orbital, and one s orbital holds 2 electrons, so they're paired. No electron is alone. Which halogen atom has the greatest electron affinity? Okay, this is whenever there's an electron affinity question on the USNCO, you have to be really careful because electron affinity is one of those periodicity things that has a lot of exceptions. They're not necessarily always predictable. Here you know it's not BRI because electron affinity generally increases as you go northeast or up and to the right of the periodic table. The reason it's Cl is because F is too small. When you add an electron onto F, basically like the electrons in the valence shell are already too close together because the F atom is already too small. So it actually has like a decent amount of shielding that makes its electron affinity still, like, I'm pretty sure the second most in the periodic table, but it's still not as good as it could be. Whereas Cl, the valence electrons are a little further spaced out, and you can actually add that last electron without as much significant shielding than you do in F. So it's actually Cl and not F. Yeah, if you were talking about electronegativity, then we'd talk about F, but different story. Okay, emission of light, you gotta go from a higher energy state to a lower energy state. So it's not 1 to 2, it's not 3 to 4. And we're talking visible light, so basically, if you want the energy, you can just do the Rydberg equation and then find the wavelength and then the frequency, and then, based on the frequency from 400 to 800 nanometers, then you could find that this is visible light. Linear, okay. So I drew them out beforehand because I just didn't want to mess up Lewis structures in the middle. But here you can see that this is just stereotypically linear. There's only 2 electron groups connected to the N, so it's very obviously linear. Here there's 5 electron groups connected to the central I, but the thing is that I'm pretty sure these are all I'm pretty sure the lone pairs are all axial, and the iodines that aren't the central iodines, oops, it looks like I'm drawing lone pairs, but those are not electrons. The non-central iodines are actually, so the lone pairs are equatorial, and the iodines are axial. So that's what makes it linear, because they're in perpendicular planes, so they don't mess with each other. Peroxy, monosulfate, anion. Oh, okay. Well, basically, you know that there is no connection between the H and the O. So you have to have... Oh, wait, no, there is. Alright, when I was taking this test, I had time to like draw it out, but right now I'm slightly blinking. So let's look up the peroxy monosulfate anion structure. So this is what it looks like. We can ignore the K plus because we're only talking about the anion. Okay, yeah, so we do have to have the OH, so I was being slightly stupid when I said there had to be no connection between the O and the H, because this is still a very weak acid, right? Because it can still exhibit proton donating properties, so the H would have to be connected to the O and not the S in order to actually be able to donate the proton. So after we take that into account, we have to realize that S can only be connected to O 4 times, like, not because of the octet rule or anything, because we're already violating that with the double bonds involved, but because you already took up one of the connections with the H, so you would have to have 4 sulfur oxygen bonds, and only B satisfies that. Okay, so next time we'll try to go through 51 through 60.